In our next segment on kinematics, we will learn about position, displacement, and distance graphs, how to construct them, what they mean, what their similarities and what their differences are. Let us first start by considering a particular example. We have a person who starts 3 meters west of a given position. Now you may recall we spoke about a universal reference point. So in this case, the flagpole becomes a universal reference point for us. So we might even label this flagpole. So they start 3 meters west. So we have a west-east situation. Generally, we make east positive and west negative. So if they start at 3 meters west, then this is where they would be starting, and that would be their initial position, XO. It takes 4 seconds to get to 2 meters east of the flagpole. So 2 meters east of the flagpole is here. So they end up here like so, and that takes them a total of 4 seconds. Then 3 seconds to get to 3 meters east. So now, whereas that took us 4 seconds, this only took 3 seconds. So immediately we can see they covered this very long distance in 4 seconds, and here almost the same amount of time to cover this shorter distance. So we could conclude that they were traveling much more slowly here. 3 seconds to get to 3 meters east, and then they sit there for 4 more seconds. So we label 4 seconds rest. And then they run westward to 5 meters west of the flagpole in 2 seconds. So they come all the way to here, and that is 2 seconds. So clearly they were running. So what would it mean to make a graph of this? Let's first make a graph of the position. We could think of having a data table here, and I've already filled in the critical times. The critical time is time 0, first of all, and that's the initial position where they started, which is -3. At time 4, they arrive at 2 meters east. And then after an additional 3 seconds, they arrive at a position of 3. So 4 seconds to here, and at the end of an additional 3 seconds, or a total time of 7 seconds, they're at a position of 3. And then they wait there 4 more seconds. 8, 9, 10, 11. At time 11, they are still at a position of 3. And then 2 seconds later, from 11 to 13, they end up back here at 5 meters west. So they end up at a position of -5. So in plotting our position, we'll make, using our key position X in blue, they start out at time 0 at a position of -3. And at time 4, they're at a position of 2. And at a time of 7, they're at position 3. And they remain there all the way to time 11. And then at a time of 13, they're at a position of -5. Now, given this information, we need to make some assumptions about the nature of their motion. The simplest assumption to make is that their speed was constant throughout all of those intervals. So if we do that, we can draw these straight lines like so. And this would be a position time graph. So if we wanted to know where they were at time 12, our best guess was that they were just about almost to 0, and they were headed westward, headed in a more westerly position. You can see that everywhere here where there's a positive slope, they're headed eastward. Here they have zero slope, they're remaining still. And here they have a negative slope, meaning they're heading in the opposite direction. We also recognized that we were traveling fairly quickly here, more slowly here, at rest here, and very quickly here. So the gradient gives us an idea of the speed. The steepest gradient we had is right here, so we have the highest speed. But it's a negative gradient, which means it's headed in the negative direction, so it's a negative velocity. Similarly here, the gradient is 0, so the velocity was 0. Here we had a shallower gradient, so slower velocity, and here a higher velocity. So that's how we would construct our position graph on this curve. I'm going to change colors now to green to illustrate the displacement. So the question we would ask ourselves, and this is the most critical one, is at the beginning, how much displacement from the original position has occurred? The answer to that question is none. There's been no displacement at time 0. So the curve starts right here at 0, 0, the origin. Now, after 4 seconds passes by, the position changes. The position changes in the positive direction by 5 units. 1, 2, 3, 4, 5. So it becomes 5 more positive. Like so. Well, what happens then? In the next 3 seconds, it goes even more, 1 more positive in the next 3 seconds. What does it do over the next 4 seconds? The displacement doesn't change, it stays the same. And what happens over the next 2 seconds? The position changes by 1, 2, 3, 4, 5, 6, 7, 8 to the negative. We're at a positive 6, so we end at a minus 2 at 13 seconds. Now again, making the same assumptions, if the speed was constant during each of these intervals, we can connect the curves. And what we observe is what you might have suspected, that these graphs are exactly the same. The only difference is they are shifted. There's a y-intercept shift. There is a y-intercept shift of 3. Y-intercept shift of 3. And what is 3? Well, the position is shifted negative 3. Well, what is that shift? Oh, reflecting the starting position. The starting position is 3 in the negative direction from the reference point. Otherwise, the graphs are identical. This is why we think of y-intercepts as being a systematic shift to the entire data. Systematic shift to the entire data. The position at any one time is given as the initial position plus the displacement. Let's see if that's true. Let's take a look at time 7. What's the position? The position is 3. Well, the initial position is minus 3, and the displacement was, initial position was minus 3, and at time 7 we're at a position of 3, so that is a change of 6, displacement of 6. We can see it visually. So minus 3 plus 6, you can see the x equals 3. That is the position at time equals 7. So those two are related simply by a shift of the initial, or correction because of the initial position. Now what about the distance? If we consider our traveler, we'll look at our distance in orange. Our person starts here. At time 0, they also have traveled 0 distance. And after 4 seconds, they have traveled 1, 2, 3, 4, 5. They've traveled the same amount. And after 3 more seconds, the distance they've covered is the same. And after 4 more seconds, the distance they've covered remains the same. They're sitting in the same position. But what happens next is what's different. The person's distance they're traveling, once they are finished taking their 4-second rest, is going to increase. And it's going to increase by a total of 8. So we can see that after 2 seconds, their position will have increased another 8, which goes off the charts here. 10, 12, 14. So our distance follows the displacement graph as long as the displacement is positive, in the positive direction. The minute the displacement shifts, or the velocity shifts to the negative direction, the distance goes in the other direction. So the distance is more. Of the 3 quantities, the distance is the greatest of the 3 quantities.